Hello, great friends. IBM is here. I hope you are doing great. Today, I would like to take you to the last unit of AS physics. It's not supposed to be the last unit, but in these videos, it's going to be the last unit, and that is going to be electricity. This is going to be electricity and DC circuits, or DC circuits and electricity. Remember, this is solved past paper questions. These are solved past paper questions where specifically we are dealing with the AS Physics 9702. We are going to look at electricity and DC circuits, that is direct current circuits, and this is specifically going to be part 1. Do not forget to subscribe, download the videos. You can watch them at your convenience. Download the document of AS. You can print it per topic so that you follow as you work on a hard copy, because it's easier to understand if you learn as you write rather than just watching. So make sure you have the document in hard copy. It is attached. The link is attached into the video in the video description, and also the link for AS paper 1 multiple choice questions has been attached or is attached in the video description. Share with your friends so that we all pass as we progress to the next level of academics. Do not forget that within this unit of electricity, we are expected to see questions about current, potential difference, EMF, resistance, questions about Ohm's law, electric power and efficiency. We shall see IV characteristic graphs many times, Kirchhoff's laws, potential dividers, and a lot more. Do not forget to share these videos with your friends. So without wasting any time, I would like to take you to the past paper questions so that we start solving the questions. So this is the document, and we are supposed to be looking at electricity. So we shall see electricity is in which page. Let's check first the page for electricity. Something's wrong with this document. Okay, so this is the content, the table of content. Remember, we have already discussed physical quantities and units. So far, we have discussed kinematics, we have discussed dynamics, we have discussed work, energy, and power, we have discussed force, density, and pressure, we have discussed deformation of solids, we have discussed waves, and I have discussed particle physics or atomic physics. So it means now we are remaining with electricity, which we are going to start, or we are embarking on just now. Note that each of these topics has been put in a playlist, so you can just check for playlists. You look for playlists, and each playlist has all the videos about that specific topic. So you can check out the playlists. If you want to do physical quantities and units, you can check for a playlist for physical quantities and units, and you see the videos in physical quantities and units, and so on and so forth. So electricity is on page 361, so we shall check page 361. 361. Okay, so here we are on page 361, and we are here to start. Number 1. The current I in a metal wire is given by this expression. My students normally prefer to write this as I equals to never, because it's easier for them to remember this equation, I equals to never, like that. State what is meant by the symbol A. So A, straight away, A stands for cross-sectional area of the wire. It's cross-sectional area of the wire. And then N. N is the number of free electrons per unit volume, or number density of free electrons. Number of free electrons per unit volume. N is not just number of free electrons, or N is not just number of electrons per unit volume. These electrons are actually supposed to be free, because in conductors, in metal conductors, electrons are considered to be free. So the number of free electrons per unit volume is what we call N. Or N is sometimes, this is the same as number density of free electrons. Number density of free electrons. Number density of free electrons. Part B, the diameter of a wire XY varies linearly with the distance along the wire as shown in the figure. Diameter varies linearly. Current I, drift speed Vx, that is on end X, and we have the same current I, drift speed, diameter d over 2, there's no drift speed given there. There is a current I in the wire at end X of the wire, the diameter is d, and the average drift speed is Vx. At end Y, the diameter is d over 2. On the figure, sketch a graph to show the variation of the average drift speed with position along the wire between X and Y. Of course, since the diameter, the diameter of the wire varies linearly, so we shall just look at what happens at the end, that is at V, at end Y. So using the general equation, we have already seen that I is equal to never, which means V is going to be the current divided by area and number density of free electrons times the charge of the electron. And we also know that the area is going to be pi times the diameter squared over 4, because they have given us diameters. So it means V at X, that is Vx, is going to be, I'm substituting area into that equation to be now 4 times the current I, divided by, I'm removing the cross-sectional area, therefore this will be pi d squared only, then times the number density n, then times the charge E, that is for Vx. Also, it implies that for Vy, it should be a similar expression. The current is the same, the number density n is going to be the same, the charge of each electron is going to be the same. So V at position Y is going to be equal to 4I divided by pi. But where there is diameter at position Y, the diameter is d over 2. So here we shall have d over 2, and this should be squared, then times n times E. So we now have two equations which we can solve. We know that at end Y, V is Vx, the drift velocity is Vx. We now want to find at end, this was at end X, drift velocity is Vx. We want at end Y, what is the drift velocity? So I'm going to divide this equation by that one. So Vy, V at Y divided by V at X is equal to, when I simplify this equation, remember this will be 4I divided by pi d squared over 4 times Ne. I'm dividing by the first equation, so I get the reciprocal. So this will be pi d squared Ne divided by 4I. And 4I cancels, Ne cancels. So it means V over Vy divided by V at X is going to be a pi d squared divided by pi d squared over 4. So the 4 goes up, and pi d squared cancels. So this is just going to be equal to 4. So it means drift velocity at position Y is 4 times drift velocity at position X. So at position Y, at position Y, the drift velocity is 4 times at the one at position X. So I just drew my point is going to be that one there. Just put a rule along 4Vx. I think it is that one. So now I'm just going to join the 2 points using a ruler. So joining the 2 points using a ruler to get, because the diameter varies linearly, so that is going to be a straight line. Okay, so it's going to be a straight line ending at, it is starting from X and Vx, and it is stopping at Y and 4 times Vx. So that is our straight line. Number next, state Kirchhoff's law, Kirchhoff's first law. So Kirchhoff's first law deals with current at a junction. So we can simply state it as the algebraic sum of currents at a junction is zero. Algebraic. Algebraic means you consider positive and negative. So you algebraic sum of currents at a junction is zero. Algebraic sum of currents at a junction is zero. Or the sum of currents into a junction sum of currents into a junction is equal to the sum of currents out of the junction. In Kirchhoff's first law, the word sum is very important because you'll be finding total currents into the junction and total currents out of the junction, and the total currents into the junction must be equal to total current out of the junction, which therefore would imply that charge is not accumulating at a junction, or charge is not just being generated at a junction. So Kirchhoff's first law is linked to a conservation of a certain quantity, state this quantity. Because current is the rate of flow of charge, then Kirchhoff's first law is related to conservation of charge. So the quantity is charge. A battery of electromotive force 8 volts and internal resistance 2 ohms is connected to a resistor X and a wire Y as shown in the figure. The resistance of X is 15 ohms. The resistance of Y is RY. The current in the battery is 2.5 amperes. Calculate the thermal energy dissipated in the battery in a time of 5.0 minutes. When we say thermal energy dissipated in the battery in that time, then we recall that power is equal to energy over time, which therefore implies that energy is going to be power times time. Since we have an electrical circuit, the power we are talking about here is electric power, where we know that power is equal to I squared times R. Therefore, this is going to be I squared R, then times T. So we can now substitute, since we have the current through the battery, we have the time, and we have the internal resistance of the battery as 2.0. So it means the thermal energy dissipated is going to be the current, which is 2.5 squared, times the internal resistance, which is actually 2.0 ohms, then times the time, which is 5 minutes. But because the answer is in joules, the time must also be changed from minutes to seconds. So this will be 5 times 60. So we can check with our calculator. 2.5 squared times 2 times 5 times 60, which is 3,750. So that is 3,750, or you can just write 3,800 to two significant figures. Then the terminal PD, the terminal potential difference of the battery, that is the PD between the terminals of the battery, the PD between the terminals of the battery. Of course, since we know the current through the battery, we can find the lost volts. And we know that EMF E is equal to the PD, the terminal PD, minus or plus, it is terminal PD plus the PD across the internal resistance, which is I times R. So it means the terminal PDV is going to be the EMF minus the PD across the internal resistance. This one we call the lost volts. This I times small r is the lost volts, which I is the current through the battery and small r is the internal resistance. So the terminal PD is going to be E minus I times R. Therefore, the terminal PD, which I'm going to call capital V, is going to be equal to the EMF E minus I times small r. So this is going to be 8.0 minus I was 2.5 and the internal resistance is also 2.0. So that gives us the terminal PD. So we shall check 8 minus 2.5 times 2, which is automatically 3. So this is 3.0. Determine the resistance Rx. Resistance Rx. So let's go back here to determine the resistance Rx. Number one, we know that this Rx resistance, resistance Ry is in parallel with the resistance X. That means the PD across X is the same as the PD across Ry, which is actually the terminal PD. So the PD across X is the same as the PD across Y, which is equal to the terminal PD, and that is 3.0 because they are in parallel. So it means we can find the current which goes through X. And since we know the total current here as 2.5 amperes, when it reaches here, it divides. Part of it goes into X and part of it goes into Y. So if I can find I in X, which is going to be the PD across X divided by the resistance of X, which is going to be 3.0 divided by the resistance of X, which is 15. That gives me the current across X. So it means that this current is going to be equal to 3 divided by 15, 3 divided by 15, I think that is 0.2. 3 divided by 15, that is 0.2. It means now the current which comes here in Y is going to be 2.5 minus 0.2. So now I will be knowing the current which is coming through Ry. And if I know the current coming through Ry, I know the PD across Ry, I should be able to get the resistance Ry. Okay. So, number one, we have said, we begin by finding the current through X. Ix is going to be 3.0 divided by the resistance, which is 15. I'm using the formula. Let me add here a small formula. Ix is going to be PD across X over the resistance of X, which is PD is 3.0 as we have seen above. The resistance is 15, and this gives us 0.20 amperes. Then to find the current through Y, current going through Y, we now subtract because at the junction the current splits. Total current entering the junction is 2.5, so we must subtract 0.2, which gives us, I think this is 0.5 amperes. So the current into wire Y is 0.5 amperes. So to find the PD across, the resistance across Y, since the PD is the same as that across X, resistance across Y will be the PD across Y divided by the current in Y. The PD is the same, which is 3.0, and the current is 0.5. So we can check this. Is it 0.5? No, sorry about that. 2.5 minus 0.2, sorry, so I think that is 2.3. This is 2.3, it's not 0.5. So this should be 2.3. So now I press my calculator to divide 2.3. 3 divided by 2.3, and that is 1.3. Yes, so RY is 1.30. Yes, 1.30. So I can simply write 1.3 ohms. That is R3. By the way, I could use a different method. Because I know that R, X and Y are in parallel. So I can find total resistance. I can find the total resistance. Then I subtract. I remove the resistance of the internal resistance. Then I can find the resistance RY. So R, this is method 2. Method 2. I know that total resistance in parallel is going to be PD, total PD, which is 3.0, over total current entering the resistors in parallel. Let me write RP to mean R in parallel. Resistance in parallel is going to be 3 divided by total current entering in parallel, which is 2.5. And I think 3 divided by 2.5 is actually 1.2. So this is 1.2 ohms. That is total resistance for parallel combination. But 1 over total resistance for parallel combination should be equal to 1 over resistance of X plus 1 over resistance of Y. So it means 1 divided by 1.2 should be equal to 1 over resistance of X, which is 15, plus 1 over resistance of Y. So when you simplify this, when you solve this, you have that 1 over resistance of Y is equal to 1 over 1.2 minus 1 over 15. Let's just solve it from this point using a calculator. So in brackets, we have 1 over 1.2 minus, open another bracket, 1 over 15. So that is what we have. Then we get the reciprocal to get RY. We get the reciprocal. So the reciprocal will be 1 divided by the answer, 1 divided by the answer, which will be 1.3. So still this is 1.3. A new wire Z has the same length but less resistance than wire Y. State two possible differences between wire Z and wire Y that would separately cause wire Z to have less resistance than wire Y. First difference, they say they have a new wire has the same length but less resistance than wire Y. Resistance of a wire is dependent on resistivity L over cross-sectional area, where the cross-sectional area is determined by the diameter or the radius. So Z could be having a larger, because Z has a smaller resistance than Y, resistance is inversely proportional to cross-sectional area. Yet cross-sectional area is directly proportional to diameter or radius. Therefore, Z could be having a larger radius or diameter or cross-sectional area. So number 1, Z has a larger radius, diameter, or cross-sectional area. Or the cross-sectional area. So if the area is greater, it means the resistance is going to be smaller. The second difference is since the length was the same, then maybe the material of Z, and if the length is the same, the only factor remaining is now the resistivity, which depends on the material. So maybe the material for Z it has a smaller resistivity, or it has a greater conductivity, because if the resistivity is small, it means the conductivity is greater. So we can say the material for Z is of a smaller resistivity. The material for Z is of a smaller resistivity or greater conductivity. Greater conductivity. So the material for Z could be having a smaller resistivity or it has a greater conductivity. That's why it has a smaller resistance. Part 2. Wire Y is replaced in the circuit by wire Z. By considering the current in the battery, state and explain the effect of changing the wires on the total power produced by the battery. First of all, you must note that power is equal to E times I. What is the effect of changing wire Y with wire Z, which has a smaller resistance? It means total resistance is actually decreasing, which means the current in the battery is going to increase. And if the current in the battery is increasing, yet the internal resistance of the battery has not changed, it means that the power dissipated in the battery must increase. So total resistance decreases, which means the current in the battery increases. Total resistance decreases. Total resistance decreases, which means the current in the battery increases. The current in the battery increases, and since power is equal to E times I, and since power is equal to E times I, so the power produced, by the battery increases. Since power is equal to E times I, since there is now more current into the passing through the battery, then the power increases because power is equal to E times I. Okay, wire X has a constant resistance per unit length and a diameter of 0.48 millimeters. Calculate the resistivity of the metal of wire X. So we know that resistance is equal to rho L over cross-sectional area. Rho is the resistivity. So it means that the resistivity is going to be equal to resistance times cross-sectional area divided by the length. So we shall just substitute. Remember area, since they gave us diameter, area is equal to pi d squared over 4. So the resistivity is going to be resistance, which is 3. No. A wire X has a constant resistance per unit length. So R over L is 3.0. So R over L is 3.0. This part here, R over L is 3.0. Then times the area. The area is going to be got from pi d squared over 4. So this will be pi times the diameter, which is 0.48 times 10 power negative 2. That is squared, divided by 4. Pi d squared over 4. So this is going to be 3 times pi times open brackets 0.48 exponent negative 2, close the brackets, but is squared, divide by 4. So we are seeing that the resistivity is equal to 5.43 or 5.4, yes, 5.43 times 10 power negative 5. So that is 5.43 times 10 power negative 5, or 5.4 times 10 power negative 5. Let me check it again. So we have 3 times pi times open brackets 0.48. Sorry, this is in millimeters. That is exponent negative 3. Sorry for that, I make mistakes. So 0.48 exponent negative 3, and that is squared, divide by 4. Sorry, this is power negative 7. Okay, that is 5.43 times 10 power negative 7. The wire X is connected into the circuit as shown in that figure. The battery has an electromotive force of 5 volts and an internal resistance of 2.0 ohms. The wire X and a resistor R of resistance 4.5 are connected in parallel. The current in the battery is 1.6 amperes. Calculate the potential difference across R. So we want the PD across R. They have given us the current through the battery as 1.6. If we have the current through the battery, then it is easy to find the PD across R, because the PD across R is the same as the PD across X since they are in parallel. So I'm saying the PD across R is equal to the PD across X because they're in parallel. However, we can find it, that is actually going to be the terminal PD. So, and this is going to be called the EMF minus the PD across 2.0 ohms. That is the lost volts. So this is going to be equal to the EMF, which is 5.0 minus the lost volts. PD across 2.0 ohms is equal to I times small r. So this is going to be I, which is 1.6 going through the battery, times the internal resistance, which is 2.0. So when you check your calculator, you have 5 minus 1.6 times 2. This is 1.8. So the PD, the potential difference there, is going to be 1.8 volts. Then determine for wire X its resistance. Determine for wire X its resistance. So now that we have the PD across it, we can find the current going through R first. So I can find current going through R. Then I get the current through X by subtracting. So that will help me to find the PD across, the resistance of wire X. Alternatively, I can find the total resistance. Total resistance, let me begin with that one of total resistance. I can find total resistance because they're in parallel. But total resistance across the parallel combination, since I have the PD, which is 1.8, over the total current entering the parallel combination is 1.6. So This is 1.8 divided by 1.6, that is 1.125. 1.125 ohms. That is total resistance for the parallel combination. Then I use 1 over total resistance for the parallel combination is going to be equal to 1 over, the other one R is 4.5 plus 1 over the resistance of X. So if I try to collect like terms, I'll just collect like terms and I find Rx by getting the reciprocal. So collecting like terms, note that, maybe let me substitute here first so that people can see that I'm substituting. So 1 over R in parallel is 1.125 minus 1 over 4.5 should be equal to 1 over resistance of X. So this is going to be open brackets 1.125 divided by 1 divided by 1.125, close the bracket, minus, open another bracket, 1 divided by 4.5. So that gives us that. Then we get the reciprocal. 1 divided by the answer, which is 3 over 2. That means the resistance is going to be 1.5. So Rx is 1.5. So this is method 1. Method number 2. Method number 2, I'm going to find the current which goes through R. I'll call it I going through R, which is going to be the PD, that is 1.8 divided by the resistance of R, which has been given as 4.5. So this is the current through R, 1.8 divided by 1.5. So this is giving me, I think that is 1.8 divided by 4.5, that is 0.4. So the current through R is 0.4, but remember the total current entering the junction was 1.6, which means now the current through X is going to be 1.6 minus 0.4 according to Kirchhoff's first law, which is going to be 1.2. Yes, 1.2 amperes. Now that I have the current through X and yet the PD across X is the same as the PD across R because they're in parallel, so it means I can find the resistance across X using V over I. That will be now a 1.8 divided by 1.2. 1.8 divided by 1.2, which gives us 1.5. So that is 1.5 ohms. So you can use either of the methods. Then its length. So we have already established earlier on that resistivity is equal to RA over L, or I'll write the common equation, resistance is equal to rho L over A. So I make L the subject. So this means L is going to be equal to RA divided by rho. So I now substitute. Since they have given us resistance per unit length, no, we don't even need that. We have the resistance of X is 1.5 ohms. We have, let's check out the resistivity. Where is the resistivity? I think we calculated the resistivity of the metal wire X. We have calculated it above here. And what remains is the area. So area is going to be pi d squared over 4. So I'm now just going to substitute R is 1.5 times the area, which is going to be pi d squared, okay, pi d squared over 4, then divide by rho. So this is going to be 1.5 times pi times the diameter was given as 0.48. 0.48 times 10 power negative 3 to change it to meters, that was squared, divide by 4. Again, divide this by resistivity, which is 5.43 times 10 power negative 7. So we can check 1.5 times pi times 0.48 exponent negative 3, that is squared. First divide by 4, then divide by 5.43 exponent negative 7. So that is 0.4999. 0.4999, which is approximately 0.50. So the final answer there is 0.50. Okay, define a volt. A volt, from the definition of PD as V equals to energy per unit charge, we can define a volt in terms of the joule for energy and then over the column for charge. So the volt is defined as the joule per column. 1 joule. A volt is defined as 1 joule per column. So PD in volts is equal to energy transferred from electrical to thermal per unit charge, where energy is in joules and charge is in coulombs. So charge energy over joule over charge, that is joules over coulombs. So a volt is 1 joule per coulomb. A battery of EMF 4.5 volts and a negligible internal resistance, it is negligible internal resistance, is connected to 2 filament lamps P and Q and a resistor R as shown. We can have a look at the diagram. The current in lamp P is 0.15 amperes. Current here is 0.15 amperes. The IV characteristic of the filament lamps are shown here. So here we have the current against voltage or current against PD characteristic. We can just have a look at it. Use the figure to determine the current in the battery. Explain your working. Note that the two batteries are actually in the two lamps are in parallel. Because the two lamps are in parallel, they should be having the same potential difference. Because the two lamps are in parallel, then they have the same potential difference. So for lamp P, the current is 0.15. So let's check. The current is 0.15 and 0.15 gives us a potential difference. Let's check downwards. 0.15 gives us a potential difference of 2.1, 2, 3, 4, 5, 6, 7. So that is 2.7. Because the bulbs are in parallel, they have the same potential difference, 2.7. Therefore, I can now check out the current through Q. So I'll just check Q is here. So that is the value for the current in Q, which I think is the scale on the vertical is 0.05 divided by 10, 0.005. So 1, 2, 3, 4. So this is going to be 0.09. That is 0.09. Every two small squares will represent 0.01. So this is 0.09. So it means we want the current through the battery. When current reaches here, it divides. Part of it takes this part, which we have seen as 0.09, and part of it is 0.15. So it means the total current which enters the junction, is the same as the current through the battery, which is the sum of those two. So, since they said explain your working, we shall start by saying that the lamps have the same PD. The lamps have the same PD of 2.7 volts because they are in what? They are in parallel. The lamps have the same PD of 2.7 volts because they are in parallel. So it means total current or current in the battery is going to be 0.15 for P plus 0.09 for Q. Total current is equal to the current through P plus the current through Q. So this gives us 0.15 plus 0.09, which gives us 0.24. Then calculate the resistance of resistor R. Resistance of resistor R. So we can go back here now that we know the current through each of these. We know the total current, which is now 0.24. And we know the PD across P and Q, or P and Q, which was 0.27. So we can now find the PD across R by just subtracting. So the PD across R is going to be the EMF, which is 4.5, minus the PD across the parallel combination, which you have seen as 2.7. So just, of course, this is going to be 4.5 minus 2.7, which gives us 1.8. That is the PD across R. So now that we know the current through R, which is the same as the current through the battery, we can just simply substitute. So this means the resistance R is going to be V over I, which is 1.8 divided by I, which is 0.24. So we have 1.8 divided by 0.24, which gives us 7.5. So R is 7.5. Okay, so that's method 1. We can use method 2, which involves using resistances. Method 2, this was method 1. Method 2, we can find the resistance across P. Since we know the PD across P, we know the current through P. The resistance is going to be PD is 2.7. The current is 0.15. I think that gives us 2.7 divided by 0.15. I think that is 18 ohms. We can also find the the resistance across Q. Since the PD is 2.7 and the current we got as 0.09. So PD is 2.7 divided by 0.09, which is 30. So that is the resistance across Q. And remember, these ones are in parallel, so we can find total resistance in parallel. I'll call it R parallel, which is, I'll just say product over sum because there are only two. So that would be 30 times 18 divided by 30 plus 18. That is total resistance in parallel. So this is going to be 30 times 18 divided by 30 plus 18, which is 11.25. So total resistance in parallel is 11.25. And remember, current equals to EMF. Current equals to EMF. Okay, so I was saying RP is resistance in parallel is 11.25 ohms. And I was saying that total current I is equal to the EMF divided by total resistance. And total resistance, remember, involves also R, which is in series. So total resistance is going to be resistance R plus the resistance in parallel. That is total resistance. So we just substitute here. The current I, which is 0.24, is equal to the EMF, which has been given as 4.5, divided by total resistance, which is R plus 11.25. So you notice that now we have only one unknown. So you notice that R plus 11.25 is equal to 4.5 divided by 0.24. So I'll just press my calculator. 4.5 divided by 11.25, divide by 0.24. Then I subtract 11.25 to make R the subject. I get 7.5. So R is equal to 7.5. So total current is equal to EMF over total resistance. But total resistance will be the sum of the resistance in parallel and the other resistance R. The filament wires of the two lamps are made from material with the same resistivity at their operating temperature in the circuit. Same resistivity. The diameter of the wire of lamp P is twice the diameter of lamp Q. Diameter is twice diameter of lamp Q. Determine the ratio length of filament wire of lamp P over length of filament wire of lamp Q. So from the formula, resistance is equal to rho L over area, and you remember area is equal to pi d squared over 4. So I'm now going to substitute and make L the subject. So L is going to be resistance times A over resistivity. Because they are from the same material, resistivity is the same. So this is going to be R times pi d squared divided by 4 divided by L, by rho. Now I'm going to make two equations because we want length of wire P over length of wire Q. So length of P over length of Q is going to be equal to resistance of P pi times, they told us that the diameter of the wire of lamp P is twice the diameter of the wire of lamp Q. So if we say for Q it is D, for P it is twice D. So this is going to be twice D and it is squared, divide by 4 rho, again divide by for Q, which will be resistance of Q times pi, its diameter is just D, divide by 4 rho. So 4 rho cancels, and our ratio now becomes, pi has cancelled, our ratio is now Rp times 4D squared divided by Rq times D squared, and D also cancels out. So this means we are now remaining with the 4 times resistance of P divided by resistance of Q. So this is going to simply be equal to the resistance of P. Resistance of P is, what is the resistance of P? The resistance of P, we have got it in the second method. The resistance of P, okay, we can find it again. Resistance of P is going to be, remember resistance is V over I. Resistance of P will be the PD, which is 2.7 over the current, which is 0.15, divide by resistance of Q. PD is 2.7, divided by the current, which is 0.09, but this is multiplied by this 4 here. So we can verify that 2.7 has cancelled out. So we remain with 0.09 divided by 0.15, which is 0.6. So this is the same as 0.6 times 4. So 0.6 times 4, which is 2.4. So the ratio is 2.4. You can also press the calculator and say, okay, open brackets, 2.7 divided by 0.15. Again, divide by, open another bracket, 2.7 divided by 0.09. It gives you 0.6, then times 4, which gives you 2.4. The filament wire of lamp cube breaks and stops conducting. State and explain qualitatively the effect on the resistance of lamp P. The filament wire of Q breaks and it stops working. So it stops conducting. So we come back here. Suppose now Q is off because it has stopped working. So if Q has stopped working, it means that the current flowing through P is going to be actually the total current in the circuit. There will be a greater current flowing through P because originally it was dividing at the junction. So it means the PD across P must be increasing, must be greater. And if the PD across P is greater and the current through P is greater, it means the resistance is going to be greater because resistance is going to be equal to the PD is equal to PD over the current. So since the PD across P is greater, then it implies that the resistance of P should therefore be, or it should be increasing. It should increase because the PD across P is greater and the current is going to increase. And if current increases, of course, when we think about this theoretically, we know that if the current through a filament lamp increases, with the time the temperature increases, and if the temperature increases, the resistance of the filament increases. Therefore, we are saying the PD across P is greater. PD across P is going to be greater, or there will be less PD across the fixed resistor. If the PD across P is greater, then the PD across R is going to be smaller. For P, the resistance is not fixed because it changes with the temperature. As more current flows through P, the temperature increases. And if the temperature increases, the resistance, the resistance is going to increase. If resistance increases, it means the PD across P is going to be greater. That means the PD across R is going to be smaller. So the PD across P is greater, or the PD across R, PD across resistor R, PD across resistor R is less. If it is greater in P, it is less in R. So that means there will be a greater current through P. So a greater current flows through P. And if a greater current flows through P, of course, since this is a filament, it also implies that the temperature is going to increase, which means the resistance will later on increase. So the resistance of P increases. So both V and I are increasing. Since there is a greater current which is flowing through P, then the resistance of P is going to increase with the time. The resistance of the filament will increase with the time. Okay. Use energy transformations. Using energy transformations, describe the EMF of a battery. So what do you mean by EMF? EMF is the energy transferred from chemical to electrical per unit charge. When we write EMF, it is energy per unit charge, but this energy is from normally chemical or other forms to electrical. So energy transferred. Energy transferred from chemical, to be specific, or it can be other forms from chemical to electrical per unit charge. Then PD is simply still energy transferred from electrical to thermal per unit charge. So energy transferred, by this time it is electrical to thermal, this was chemical to electrical. So PD is energy transferred from electrical to thermal per unit charge. Energy transferred from electrical to thermal per unit charge, that is PD. A battery of EMF 6 volts and negligible internal resistance is connected to a network of resistors and a voltmeter as shown in the figure. Resistor Y has a resistance of 24 ohms and Z has a resistance of 32 ohms. The resistance Rx of the variable resistor is adjusted until the voltmeter reads 4.8. So the PD across Z is 4.8 volts, which means the PD across the parallel combination should be 6 minus 4.8, which is 1.2 volts. The resistor Rx of the variable resistor is adjusted until the voltmeter reads 4.8. Calculate the current in Z. Calculate the current in Z. So since they have given us the PD and we have the resistance, then the current is going to be simply PD over resistance, which is 4.8 divided by 32. 4.8 divided by 32, which is 0.15. Then calculate the total power provided by the battery. Total power provided by the battery. Power provided by the battery is normally EMF times the current, or it can be, you can use IV or I squared R and so on and so forth. So this is going to be the EMF, which is 8. Since the current in Z is the total current through the battery, so the power is going to be 8 volts. No, 6 volts. The EMF is 6.0 times 0.15. 6 times 0.15, which is 0.9. So the power is 0.9 watts. Then the number of conducting electrons, that move through the battery. So we know that charge is equal to the number of conducting electrons times the charge of one electron, which is current times time. That is the charge. So the number of conducting electrons is going to be current times time divided by the charge of one electron. So the current is 0.15. The time is 25 seconds divided by the charge of one electron, which is 1.6 times 10 power negative 19. 0.15 times 25 divided by 1.6 exponent negative 19. So that is 2.3 times 10 power 19. So this is 2.34 times 10 power 19. 2.34 times 10 power 19. Then total resistance of X and Y. Total resistance of X and Y. So since we have the total current entering this junction here, we have total current entering the junction there, which is 0.15. So we can just find the total resistance of the circuit minus total resistance of the circuit minus the PD across Z. I mean the resistance of Z. That will give us the total resistance of XY. So current, remember, total current is equal to EMF divided by total resistance, RT, which means total resistance in the circuit is going to be the EMF, that is 6.0 over total current, which is 0.15. So this is 6 divided by 0.15, that is 40. So total resistance is equal to 40. Total resistance is equal to 40 ohms. But remember, total resistance is equal to resistance of Z plus the resistance of XY, which were in parallel. So that means resistance of XY is going to be equal to, since they are in series, is going to be 40 minus 32, which is equal to 8.0 ohms. So this is going to be 8.0 ohms. That is the resistance X. That is the total resistance of X and Y in parallel. Alternatively, we can find the PD across the parallel combination. This was method 1. Method 2, I can find the PD across XY, which is 6 minus 4.8, that is 1.2 volts. Then I have the total current entering the parallel combination as 0.15. So resistance RXY is going to be total PD in XY, which is 1.2, divided by total current, which is 0. Total PD across XY, which is 1.2, divided by, this is going to be 0.15. 1.2 divided by 0.15, which is 8. Then find the resistance Rx. Since we have total resistance and we have resistance of Y, we can just use a simple formula for total resistance. In parallel, 1 over resistance in parallel is equal to 1 over Rx plus 1 over Ry. Total resistance in parallel is 8, so I will say 1 over 8 is equal to 1 over resistance of X, which is Rx, plus resistance of Y, which is 24. So it means 1 over resistance of X is equal to 1 over 8 minus 1 over 24. So this is going to be 1 divided by 8 minus 1 divided by 24, which is 1 over 12, and then we get the reciprocal. So this one is equal to 1 over 12. Then when we get the reciprocal, it means Rx is equal to 12. So this is going to be 12 ohms. The resistance Rx is now decreased. The resistance Rx is now decreased. State and explain the change, if any, to the reading on the voltmeter. When we reduce Rx, what happens to the reading of the voltmeter? Of course, reducing Rx means total resistance decreases. And if total resistance decreases, it means the PD across X and Y becomes smaller, which implies that the PD across Z must be increased because total PD should be equal to the EMF. So total resistance XY becomes smaller when X is reduced. And remember, PD is equal to I times that resistance. If R has become smaller, the PD is smaller, R between XY. So PD XY decreases, and if XY decreases, it means Z, PD across Z must increase so that the total is still 6. Therefore, you just simply say total resistance decreases, so the voltmeter reading increases. So total resistance decreases. Total resistance decreases, so the voltmeter reading increases. Or simply say PD across XY decreases because resistance XY decreases, so PD across Z must increase. Total resistance decreases, so the voltmeter reading increases. Or I am saying the PD across XY decreases because the resistance XY decreases. And so the PD across Z must increase. Okay, state Kirchhoff's second law. Of course, we saw the first law was concerned with charge. The second law is concerned with energy, conservation of energy. That is, in a closed loop, the sum of EMFs is equal to the sum of PDs. So in a closed loop or in a closed circuit, in a closed circuit or loop, it must be closed. The sum of EMFs should be equal to the sum of PDs. In a closed loop or in a closed circuit, the sum of EMFs should be equal to the sum of PDs. Remember, we have defined EMF in terms of energy. We have defined PD in terms of energy. That means Kirchhoff's second law is a consequence of conservation of energy. It's a consequence of conservation of energy. Okay. Two batteries, each of electromotive force 6 volts and negligible internal resistance, are connected in series with 3 resistors as shown here. So you can have a look at the diagram. So resistor X has resistance 4 ohms, resistor Y has 1.5. The resistance R of the variable resistor is changed until the voltmeter in the circuit reads 0. That means the potential here is the same as the potential there. So the potential difference between those 2 points is 0. So it means, of course, since the voltmeter, the battery has negligible internal resistance. Okay. So calculate the current I in the circuit. Calculate the current I in the circuit. So you can choose a simple loop and try to find the current. We shall choose a loop here where everything is given. So the current here, because the potential difference between the 2 points is 0, so the current here is also going to be I. So I'm going to choose an anti-clockwise loop. That is my loop. So moving around anti-clockwise, the current through this is still I. So we are only considering this part here. The potential difference here is 0. And here the EMF is 6. So the sum of the EMFs is equal to the sum of the PDs for a closed loop. So we are going to just sum the EMFs, which will be 6.0 should be equal to the sum of the PDs, which is the other one is 0 plus we have a resistance 4. Remember, PD is equal to I times R. So this is going to be 4 times I. That will be the PD. Therefore, the current I is going to be 6.0 divided by 4. 6 divided by 4, which is 1.2. So the current I is 1.2 amperes. Then determine the resistance R. Determine the resistance R. So to find the resistance R, I have two ways of doing it. I can consider just this loop here. Since I already have I can consider that loop, and I will set is again anti-clockwise. The PD here is 0. The PD here will be 1.5 times I. The EMF here is 6. The PD here will be I times R. Then I sum up to get R. So using Kirchhoff's second law, considering that loop, there's only one battery of 6 volts, so that will be 6 equaling to the PD across 1.5. The current is in the same direction with the loop, so it is positive. So I'll say 1.5 times I plus the PD across R. It is in the same direction as the current is in the same direction as the loop. This current I is the same current flowing. So it will be I times R positive. So this will be I times R positive. But we have already found I as 1.5. Therefore, 6 is going to be 1.5 times 1.5 plus 1.5 times R. So we just collect like terms. I will say 6 minus 1.5 times 1.5 divided by 1.5, which is giving us 2.5. So R is 2.5 ohms. Alternatively, I could use a larger loop in the circuit. I'm going to use a larger loop. Let me change even the color. I could use a larger loop in the circuit, which is still anti-clockwise. And I will say sum of EMFs. When I use a larger loop, I have ignored V. I've ignored the voltmeter. So the sum of EMFs, because they are in the same direction, I will have 6 plus 6 because they are joined in the same way. 6 plus 6, that is sum of the EMFs. Because the sum of PDs for this one to be 4 times I plus for this one to be 1.5 times I plus for R it is again I, R times I. So we have a common factor I which is 1.5. So I'll just say 12 equals to 1.5 into 4 plus 1.5 plus R. Then we just simplify this with our calculator. Twelve divided by 1.5, then minus in the brackets I have 4.5, which is 12 divided by 1.5, then minus 4 plus 1.5 is 5.5. What am I doing? 12 divided by 1.5. Okay, that is 8 minus 5.5, which is 5 over 2, which is 2.5. That is going to be our resistance R. Resistor X and resistor Y are wires made from the same material, which means resistivity is the same. The diameters of the wires of X is twice the diameter of the wire of Y. So if diameter of y is d, diameter of x is going to be twice d. Determine the ratio average drift speed of free electrons in x over average drift speed of free electrons in y. So let's go back to the basics first. First of all, resistance is equal to rho L over cross-section area A. So they have told us they are from the same material, so resistivity is the same. The diameter is different. We can assume that, of course, if the diameter is different, nothing is mentioned about the length. So we can first leave the length there. But then also we know that current I is equal to never, NEVA, which means V is directly proportional to I, and V is inversely proportional to A. So V is directly proportional to the current, or V is equal to the current divided by NE times A. The resistance is directly inversely proportional to area, and the drift velocity is also inversely proportional to area but directly proportional to the current. So they are telling us that the diameter of the wire is twice d, the diameter of the wire is 2d. Sorry about that, my computer had failed to respond. Okay, so we're saying resistance is directly proportional, inversely proportional to area, and we're also seeing that V is equal to I over NEA. They gave us diameter, we shall remove A. Drift velocity is going to be I over NE, where there is I have pi d squared over 4. That is for area, pi d squared over 4. Let me make this clearer. So for area, we have pi d squared over 4. So that means drift velocity is going to be 4I divided by number density times the charge E times pi d squared. So let's come up with now two equations. So the ratio is going to be drift velocity of x over drift velocity of y, which is for x. It is going to be 4I divided by number, charge density, charge of each particle times pi. For x, they say the diameter is twice, so we shall put there 2d and it is squared. Divide by 4y to be 4I divided by NE pi, its diameter is d and it is squared. So we're now simplifying, we just cross multiply. We change we get the reciprocal. So the ratio is going to be equal to 4I over NE pi into brackets 2d squared times NE pi d squared divided by 4 times I. So 4I cancels, NE pi cancels. So you remain with the d squared divided by 4d squared, which is equal to 1 over 4. So the ratio is 0.25. 0.25. So that is the ratio. Okay. The resistance R of the resistance R of the variable resistor is now increased. State and explain the effect of the increase in R on the power transformed by each of the batteries. They have increased the R. The resistance of the variable resistor is now increased. State and explain the increase, the effect of the increase in R on the power transformed by each of the batteries. So they have increased R. Remember, power is equal to V squared divided by R, power transformed by the battery. If R is increased, remember the resistors are all in series. It means total resistance increases. And if the total resistance increases, it means the current flowing through the batteries decreases. And if the power transformed in the batteries, is I squared R, if the total resistance increases, the current flowing decreases, but remember this is squared. So it means the power dissipated is going to be, this is power dissipated when there is internal resistance. We are saying if the total resistance increases, it means the current actually decreases, and the power transformed in the battery is E times I. If the current flowing decreases, it definitely means the power decreases, because power transformed in the battery is I times E, or E times I. Or alternatively, if the EMF is not changing, and so this is going to be E squared over R. If the EMF does not change, it is not changing, and the resistance R increases, you notice that the power actually decreases. Therefore, we are saying that total circuit resistance increases because they're in series. And if that is true, it means the current flowing decreases. The current I decreases. And since the power transformed in the battery is E times I. So it means so the power transformed decreases. So power transformed decreases. The power transformed decreases. Okay. The resistors of R1, R2, and R3 are connected as shown in the figure. Total current in the combination of resistors is I, and the PD across the combination is V. Show that the total resistance R of the combination is given by 1 over R equals to 1 over R1 plus 1 over R2 plus 1 over R3. So this is a junction. When current reaches here, it must be dividing. So we shall say I1, this is I2, and this is I3. Therefore, for resistors joined in parallel, total current I is the sum of I1 plus I2 plus I3. What is the same is the PD. So the PD across is the same. PD across each is the same. And remember the PDV is equal to I times R, which means the current I is equal to V over R. Therefore, we are now going to substitute. For I, it is going to be V over R. For I1 to be V over R1 plus V over R2 plus V over R3. So there is a common factor of V on the right hand side. So V over R is equal to V into 1 over R1 plus 1 over R2 plus 1 over R3. So V cancels out, and you remain with 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So that is the equation required. A battery of EMF 6 volts and internal resistance R is connected to a resistor of resistance 12 ohms and a variable resistor X as shown in the figure here. We can look at the figure. By considering energy, explain why potential difference across the battery terminals is less than EMF. Here they said it has internal resistance R. That means the EMF is going to be equal to the terminal PD plus the PD across the small resistance R. So that means The PD across the battery is the terminal PDR, which is going to be the EMF minus VR. Because the battery has internal resistance, it means the terminal PD is not the same as the EMF. So we can say EMF is the total energy available. Total energy available per unit charge. Total energy available per unit charge, and energy is dissipated in the internal resistance. And energy is, or some energy is dissipated in the internal resistance. Because some energy is dissipated in the internal resistance R, it means the PD across the battery or terminal PD is not going to be equal to the EMF. So terminal PD is less than the EMF. Because some energy is wasted in the internal resistances, the terminal PD will be less than the EMF itself. A charge of 2.5 kilocoulombs passes through the battery. Calculate the total energy transformed by the battery. So we have seen that energy transformed by the battery, or the EMF, is equal to the energy transformed by the battery per unit charge. Energy transformed by the battery per unit charge, that was EMF. So this means the energy transformed is going to be the EMF times the charge. EMF times the charge. So the EMF is 6.0 times the charge, which is 2.5 times 10 power 3. 6 times 2.5 exponent 3. That is 1,000. It is actually 15,000. Calculate the number of electrons that passes through the battery. Number of electrons passing through the battery. Remember, we said total charge is equal to the number of electrons times the charge of one electron, which total charge is equal to current times time. So the number of electrons is going to be equal to the current, or they gave us the charge. So I'll just say charge divided by E. So the charge is 2.5 times 10 power 3 divided by 1 electron, 1.6 times 10 power negative 19. So 2.5 exponent 3 divided by 1.6 exponent negative 19. So that's 2.5 exponent 3 divided by 1.6 exponent negative 19. Okay, that's 1.56 or 1.6 times 10 power 22. The combined resistance of the two resistors connected in parallel is 4.8 ohms. Calculate the resistance of X. They gave us the other resistor as 12, so they are in parallel, and their combined resistances were 4.8. So 1 over 4.8, that is total resistance, is equal to 1 over 12 plus 1 over Rx. That's resistance of X. So 1 over Rx should be 1 over 4.8 minus 1 over 12. So let's check with the calculator. 1 divided by 4.8 minus 1 divided by 12. Then we get the reciprocal. We get the reciprocal, that's 1 divided by the answer, which is 8. So 1 over Rx is 1 over 8, which means X is 8 ohms. Use your answer in B Roman 3 to determine the ratio power dissipated in X over power dissipated in the 12 ohm resistor. So power dissipated in any resistor is equal to the PD across the resistor divided by the resistance of that resistor. Because they're in parallel, V is the same. So the ratio will be equal to PD squared over resistance of X divided by PD squared over resistance of 12 ohms. So this is going to be V cancels, resistance of 12 ohms goes up. So it is 12 divided by resistance of X, which is 8. So it is 12 divided by 8, which is 3 over 2, which is 1.5. So the ratio is 1.5. The resistance of X is now decreased. Explain why the power produced by the battery is increased. The resistance of X is now decreased. That means total resistance is going to decrease. And if total resistance decreases, the power produced by the battery, of course, power produced by the battery is going to be E times I. If total resistance decreases, it means the current flowing through the battery increases. And if the current increases, it means the power increases. If resistance X is decreased, total resistance decreases, which means the total current is going to increase. And the power transformed by the battery is E times I. So that means the power transformed increases. So we can say total circuit resistance, total circuit resistance, total circuit resistance decreases, total circuit resistance decreases. So total current I increases, and power is equal to E times I. Hence power increases. Alternatively, you can look at power as being equal to E squared over R. If total circuit resistance decreases, automatically power increases if E is constant. State what is meant by electric current. Electric current, of course, electric current is the flow, because we know that charge is equal to IT, or I is equal to Q over T. Current is the rate of flow of charge carriers. So this is rate of flow of charge carriers. The rate of flow of charge carriers. The charge carriers could be electrons, could be any other particles in motion. So the rate at which they flow is going to constitute what we call current. A metal wire has length L and cross-sectional area A as shown in the figure. I is current, N number of free electrons per unit volume, V is the average drift speed of a free electron, and E is the charge on the electron. State in terms of A, E, L, and N an expression for the total charge of free electrons in the wire. Total charge. So charge is equal to, we have the number of free electrons per unit volume is N. Number of free electrons per unit volume. So total number of free electrons is going to be N times the volume, which volume is cross-sectional area times L. That is the volume. But the charge of each, this is the total number of electrons in the whole volume. But then each electron has charge E. So the expression is going to be N, A, L, E. Use your answer in Roman 1 to show that the current I is given by that equation. Current I. So we are going to use our equation there. First of all, let T be the time taken for electrons to move a given length L. So I'm going to let T be the time for electrons to move length L. Let T be the time for electrons to move length L, and that means T is going to be equal to the length, which is the distance L, over the drift velocity V, which means that okay, that is T. So by definition, we know that current is equal to the charge over time T, and we have seen the total charge is NALE. So it means this is going to be equal to NALE divided by T. But remember, T is L over V. So this means I is going to be NALE divided by T, which T is L over V. So this is going to simplify to NALE over 1 times, we get the reciprocal, which will be V divided by L. You notice that L cancels out. So that means the current I is going to be equal to NAE times V as required. A metal wire in a circuit is damaged. The resistivity of the metal is unchanged, but the cross-sectional area of the wire is reduced over a length of 3 millimeters, as shown in the figure. The wire has diameter D at cross-section X and diameter 0.969 D at cross-section Y. The current in the wire is 0.5 amperes. Determine the ratio average drift speed of free electrons at cross-section Y over average drift speed of free electrons at cross-section X. So we have earlier on seen that I is equal to never. That means V is going to be equal to I divided by NEA. Because they're in series, the current is the same. Because N is going to be the same and E is the same, so we shall simply say V is equal to a constant divided by A. So we shall say V at X divided by V at Y should be equal to the constant K divided by area of X times, I get the reciprocal because I'm dividing by that of Y, so it will be times area of Y divided by the same constant. We said I over NE will be the constant. So that constant will always cancel out. So the ratio Vx over Vy will be equal to area of Y, area at Y over area at X. And also remember that area is equal to pi d squared over 4. So this is going to be 4y. Area is going to be pi, where there is d, I'll put 0.69 d, and this is squared divided by 4. Then for x, the area will be pi, the diameter is d, so I will say d squared over 4. And 4 cancels, pi cancels. So I only remain with 0.69. I think I reversed this. This is not x, it is supposed to be y according to the question. But anyway, I will get the reciprocal later on, but this is going to be y, this is x. So this will be x and this will be y. This will be y, this is x. So this is actually going to be the other round. Area V at X at Y over V at X. So this would be now the reciprocal, which is area at X over area at Y. So at X, diameter is D, so this is just going to be pi D squared over 4. And at Y, diameter is 0.69 D, so this will be pi 0.69 D squared divided by 4. So this is going to give us 4 cancels, pi cancels to remain with D squared over 0.69 D, but that is squared, which is the same as 1 over 0.69 squared because D squared cancels. So you have 1 divided by 0.69 squared, which is 2.1. So the ratio is 2.1. The main part of the wire with the cross-section X has a resistance per unit length of 1.7 times 10 power negative 2 ohms per meter. For the damaged length of the wire, calculate the resistance per unit length. So we know that resistance is equal to rho L over A. Now we want resistance per unit length, that is R over L. So this implies that resistance over L is equal to rho over A. Therefore, we shall say that resistance per unit length, I'm going to come up with two equations. So I'll say resistance per unit length of wire Y is going to be rho divided by area of Y. And resistance per unit length of wire X is given as 1.7 times 10 power negative 2, but it is equal to rho divided by area of wire X. So I want the resistance per unit length for the damaged section, which damaged section is for Y. So I'm going to just combine two equations or divide them. So resistance per unit length of Y divided by for X, which is 1.7 times 10 power negative 2 is equal to rho over area of Y divided by rho over area of X. So we get the reciprocal. So I'm going to come here. Resistance per unit length is going to be rho cancels. And because we get the reciprocal, this is going to be equal to rho over AY times AX over rho. So rho cancels. So this is going to be equal to area of X over area of Y. And we have seen that the ratio of area of X over area of Y is equal to 2.1. So by the way, this is times. Remember, there is this value here in the denominator. So we shall say times 1.7 times 10 power negative 2. Therefore, it will become AX over AY is 2.1 in the previous equation times 1.7 times 10 power negative 2. So the answer times 1.7 exponent negative 2, which gives us 0.036 or 3.6 times 10 power negative 2. So note I quoted resistance per unit length of Y divided by resistance per unit length of X. This is equal to rho over L over area for Y divided by rho over area for X. Then I did the algebra. So I came up with a simple expression that resistance per unit length for Y is equal to area of X over area of Y times resistance per unit length for X. So when you substitute, you get 3.6 times 10 power negative 2. Then the power dissipated. Of course, we know that power is going to be equal to I squared times R. Power is I squared times R. We want power dissipated in the damaged section. So the resistance per unit length is that. So we just need the length itself to find total resistance. Total resistance is going to be resistance per unit length, which is 3.6 times 10 power negative 2, then times the length. Length of the damaged section is 3 millimeters, so it will be times 3 times 10 power negative 3. That is total resistance. So the power is going to be the current. They gave us the current as 0.5. So the current is 0.5 squared times 3.6 times 10 power negative 2 times 3 times 10 power negative 3. 0.5 squared times 3.6 exponent negative 2 times 3 exponent negative 3, which gives us 2.7 times 10 power negative 5. 2.7 times 10 power negative 5. The diameter of the damaged length of the wire is further decreased. Assume that the current in the wire remains constant. State and explain qualitatively the change, if any, to the power dissipated in the damaged length of the wire. So we have seen that power is equal to I squared times R. The current remains constant. And R is inversely proportional to the area, which area is 4 pi d squared, pi d squared over 4. That means R is inversely proportional to the square of the diameter. So they have said the length of the wire is further decreased. Resistance is equal to rho L over cross-sectional area. The diameter is the one which has been decreased. That means the cross-sectional area has been decreased further. And if the cross-sectional area is decreased, it means the resistance actually increases. And if the resistance increases from power equal to I squared R, it means the power also increases. Therefore, cross-sectional area increases, cross-sectional area actually decreases. Cross-sectional area decreases when the diameter is decreased, so resistance increases. So resistance increases. And from power equals to I squared R, so power increases. The power increases. As simple as that. Okay, let's stop with this page number 4. 3 cells of electromotive force E1, E2, and E3 are connected into a circuit as shown here. The circuit contains resistors R1, R2, R3, and R4. The currents in the different parts of the circuit are I1, I2, and I3. The cells have negligible internal resistance. Use Kirchhoff's laws to state the equation relating I1, I2, and I3. That is at the junction. You can look for a convenient junction. Perhaps you can look at junction Y. At junction Y, you see that I3 is entering, I1 is leaving, and I2 is leaving. So the sum of currents entering the junction should be equal to the sum of currents leaving the junction. Therefore, we can say I3, which is entering, is equal to I1 plus I2, which are leaving. Then E1, E3, R1, R3, R4, I1, I3 for the loop W. We are moving from W to X, Y, Z, back to W. X, W, X, W. We are moving W, X, Y, Z, back to W. That is anti-clockwise. That is clockwise. From W, X, Y, Z, back to W. So it means we are ignoring the internal components. So let me just change the color for the loop. So we are ignoring the internal components. So we are moving in that direction. So the sum of EMFs, we have only this one and this one. And you are seeing that the current through them is in the same direction as our loop. So we just sum them up. So it will be E1 plus E2, that is E1 plus not E2, E3. That is the sum of EMF, should be called the sum of the PDs. The current here is I3, so this PD is I3 times R3. The current here is still I3, so this speed is I3 times R4. The current here is I1, this speed is I1 times R1. And that's all. Because the currents are in the same direction as our loops, they will all be positive. So we just say I1 times R1 plus I3 times R3 plus I3 times R4. That is the sum of the PDs. Then we are looking at E1, E2, R1, R2, I1, and I2 in the loop Y, Z, W, Y. Let's look for that. Y, Z, W back to Y. So the loop we are talking about, I'll use a different color for that loop. It is just this loop here. From Y to Z to W back to Y. It is still clockwise. It is still clockwise. It is still a clockwise loop. So there are only two cells. There is E1 and E2. And when you move around the loop, you see that the cells are in opposite directions. The current through the cells is in opposite direction, so we subtract these EMFs. If E1 is positive, E2 is negative. So we shall say E1 minus E2. E1 minus E2, because the current through them are in the opposite direction. In fact, the current through E2 is in the opposite direction to our loop, but the current through E1 is in the same direction to our loop. So E1 minus E2 is equal to the sum of PDs. For R1, the PD will remain I1 R1 because the current is in the same direction as the loop. But for R2, the current is in the opposite direction to the loop. So the PD here will be I2 R2, but is in the opposite direction to the loop. So it will be minus. So this will be equal to I1 R1 minus I2 R2. So that is the sum of the PDs. The minus is because the current in the R2 is in the opposite direction to the loop. So it is going to be negative. Define the ohm. Of course, the ohm is a unit for resistance. So V is equal to I times R. R is equal to V over I. The units of V are volts. The unit of I is amperes. So the ohm is a volt per ampere. So the ohm is a volt per ampere. A volt per ampere. That is the ohm. Okay. Wires are used to connect a battery of negligible internal resistance as shown here. So we are seeing the wires. The lamp is at its normal operating temperature. Some data for the filament wire of the lamp and for the connecting wires of the circuit are shown in the figure. Show that the resistance of the filament wire over the resistance of the connecting wires equals to 1000. So to start with, because I don't have enough space, I will utilize the space available. Resistance is equal to rho L over area. And we know that area is equal to pi d squared over 4 because they have given us values for diameter. So I'm going to combine the two equations. So resistance for the filament over resistance for the connecting wires is going to be where there is rho L. Now I'm combining. Let me first combine. So resistance is going to be 4 goes up, rho L. Where there is area, you have pi d squared over 4, where the 4 has gone up. So for filament, it will be 4 rho L over pi d squared, because the diameter of filament is d. Divide by For the connecting wires, it will be 4. Resistivity is given as 0.028 times rho. Then times the length, which is given as 7.0 times L. Divide by pi, where there is diameter, I'll put there 14. D, but is squared. I'm now going to simplify. I'm going to simplify. Of course, 4 rho, 4 cancels out in the numerators, and rho cancels out, L cancels out, pi cancels out. So the 14D goes up. So I'll have 14D, which is squared, divide by, in the numerator, I remain with D squared times 0.028 times 7. I just did this part here, divide by the other one, reciprocal when you remove the division sign. So this becomes 14D squared, or there is a D here. Where is the D? Yes. 14 squared times D squared divided by 7 times 0.028 times D squared. So D cancels out, D squared cancels out. So I remain with 14 squared divided by 7 times 0.28. Sorry, 14 squared divided by 7 times 0.028, which is 1000. Use the information in Roman 1 to explain qualitatively why the power dissipated in the filament wire of the lamp is greater than the total power dissipated in the connecting wires. So the wire, of course, the current is the same because they are in series. The connecting wires and the filament are in series. So number one, the current is the same in the connecting wire and the filament. That's one. The current is the same in connecting wires and the filament. In the connecting wires and the filament wire. That's number one. But the lamp has a greater, the lamp is having a greater, or the filament wire has a greater resistance, because when you look at this expression here, we are seeing that the resistance of the filament is 1000 times the resistance of the connecting wires. Resistance of the filament is 1000 times the resistance of the connecting wires. But resistance of the filament wire is greater. The resistance of the filament wire is greater. And also note that power is equal to I squared times R. If current is the same, the resistance, where the one which has a greater resistance has the greater power. The resistance, but the resistance of the filament wire has a greater resistance. But the filament wire, because use the explain quantitative where the power dissipated in the filament is greater. So the resistance of the filament wire is greater, and from power is equal to I squared R, so greater power in the filament wire. Expect greater power in the filament wire. Okay. The lamp is rated 12 volts, 66 watts. Use the information in Roman 1 to determine the total resistance of the connecting wires. Okay, so power, we know power is equal to V squared over R. You can check for the filament. For the filament wire, resistance is going to be equal to 12 squared divided by the power, which is 6, because the lamp is rated that. So this is going to be 12 divided by 6, 12 squared divided by 6, that is 24. So the resistance of the filament wire is 24 ohms. And for the connecting wires, therefore, for connecting wires, remember they are two on either sides. For the connecting wires, because the resistance of the filament is 1000 times the resistance of the connecting wires. So for the filament, if it is 24, then the other one is 1000 times the resistance of the connecting wires. So resistance for the connecting wires, this was RF. Resistance for connecting wires is going to be 24 divided by 1000. So now we can find total resistance. So total resistance. Total resistance. They want total resistance of connecting wires. So total resistance of connecting wires is going to be equal to simply 24 divided by 1000, which is 2.4 times 10 power 24 by 1000, 2.4. What is that? 2.4 times 10 power negative 2. 2.4 times 10 power negative 2. So that will be the resistance, 2.4 times 10 power negative 2 ohms. And lastly, the diameter of the connecting wires is decreased. The total length of the connecting wires and resistivity of the metal of the connecting wires remain the same. State and explain the change, if any, that occurs to the resistance of the filament wire of the lamp. So resistance is equal to rho L over cross-sectional area, which is equal to 4 rho L over pi d squared. So the diameter of the connecting wires is decreased. When the diameter is decreased, it means the resistance of the connecting wires increases. That's the starting point. Resistance of connecting wires. Resistance of connecting wires increases. If the resistance increases, what happens to the current flowing in the circuit? It means the current in the circuit or current in the filament wire decreases because the current is the same. So the current in the circuit or in the filament wire decreases. The current in the circuit or the current in the circuit or the filament wire decreases. And if the current in the filament wire decreases, it means the PD across the filament wire decreases. So it means the resistance of the filament wire is actually decreased. So if the current in the filament wire decreases, or the PD across the filament wire decreases, since the PD in the wires increases, it means the resistance of the filament wire decreases. So the resistance of the filament wire decreases. Of course, we even know this from relating it to temperature. When the current flowing in the wire is small, the temperature is relatively lower, so the resistance is going to be lower. But if the current increases, the temperature of the filament wire increases, so the resistance also increases. So the resistance of the filament wire decreases because resistance of the connecting wires increases, which means the current in the filament wire decreases. Remember, the current in the filament wire is the total current in the circuit because the wires are joined in series with the lamp. So the current in the wires is the same as the current in the filament. So since the current decreases, it means the current in the filament also decreases. And if the current in the filament decreases, it means the PD across the filament wire decreases, and therefore the resistance of the filament wire decreases. So the resistance of the filament wire decreases. Okay, let part 1 stop there. We shall start from that point in part 2. Have a blessed day.